Good evening, everyone. Today we'll start with the next topic, optical microscopy. Optical, as we all know, it deals with the visible light. In general, in microscopic techniques, the visible light we mean 400 nanometer to approximately 700 nanometer. Okay. The word micro, it comes from the Greek word micro, which means small. Okay, and then scopy, it means view. Okay, or to see. So if you look over here, what is happening? The word microscopy means to see small objects. In biology, we basically view bacteria, mammalian cells. Okay, we can look into the architecture of the food products. Cellular organization in plants, etc. Okay, so herein what we mean is that when we talk about that to visualize small objects, herein in the case of biology we means we want to visualize the biological small biological objects which cannot be visualized using normal eye. Using naked eyes. Okay. So when we talk about optical microscopy, that means while we are visualizing these small objects, we are using visible light. Okay. And that is the whole meaning of optical microscopy. Okay. In your high school, you must have studied about the convex lenses. Okay, so herein what we have, as I told you, we have this convex lens, we have f1 which is the focal length, and then we have another this thing, we have 2 of f1 over here. Similarly on the other side also we can have say f2. And say we are having 2 of f2. Now if I have a object over here, it will be forming an inverted image like this, right? Now, if I bring this object, say at f1, we will be getting an more bigger image. Okay. However, if we bring this object further nearer to the lens, the first one will follow in this way, and if you see, there is a divergence over here, so no image will be formed on the other side of the this convex lens. In this case, we will get an image on the same side of the object, and they will be having directions in the they will be having what you call in the same direction. They will not be, it will not be an inverted image. However, it will be an magnified image. On the say cases 1 and 2, we will be getting the images on the other side of the lens, and both the lenses, both the images will be inverted images. This 1 dash and 2 dash objects, they will be having inverted images. Okay. Whereas in the third case, when the object is quite nearer to the lens, it will be forming the image on the same side of the lens, and it will not be inverted, it will be having the same orientation. Okay, this is one of the basic things which we need to remember. Okay, now in case of 1 and 2, when we have placed the objects at the location 1 and 2, we have seen that the image of the object has been magnified. Even though the image is inverted, but we have a magnification of the image. Okay. Now, due to this reason, is we call this single lens magnification as a simple microscope. Okay. So single lens magnification, it is also regarded as a simple microscopy. Okay. However, in our case, in this optical microscopy chapter, we will be discussing about compound microscope. We will be discussing compound microscope. In the compound microscope, what is the basic architecture? The basic architecture is something like this. We have a source. Okay. Just above the source, we have a diffuser. Then we have a condenser lens, or in general we called it condenser. So what this condenser does, this condenser, it collects the light from the source which is passing through the diffuser, and it collects it and it condenses the light. Just above this condenser, we will be having a mechanical stage. Okay, over this mechanical stage, we will be having our sample specimen. The sample specimen, we will be basically, the light will be passing through this sample specimen, and usually you will see that we use glass lights to hold the specimen. Okay, now through this the light will be passing through, and this light, it will be collected through an objective lens. Then there will be a path optical tube which will allow this collected objective collected light to pass through the optical tube, and then we will be having an eyepiece lens. Okay. Now this is the basic architecture of a compound microscope. And when we do the compound microscopy, we have different modes. This mode, what I have shown, it is in general called bright field microscopy. Then second, we have dark field microscopy. Third, we have fluorescence microscopy. Fourth, we can have polarizing microscopy. In short, we write it as PLM. Okay, and there are many other things, oblique microscopy and other things are there. Then for analyzing this bacteria, we can have say a phase contrast microscopy. Okay, so there are many other microscopic techniques are also there. So which we will be discussing. Some of them we will be discussing. It is not possible to discuss all the things in a very short time. So what we will be doing is that we will be taking up some of the microscopic techniques and we will be discussing some of these. Okay. So background, a microscope, as I told you, this word has been derived from the ancient Greek words micros, which means smalls, and this scopy, it has been derived from the word scopian, which means to look or to see. So it is a laboratory instrument that is used to examine objects that are too small to be seen by the naked eye. Okay. Microscopy is the science of investigating small objects and structures. Okay. The most common microscope and the first to be invented is the optical microscope. Apart from this optical microscope, there are other types of microscopes like electron microscope, scanning probe microscopes. Okay. So fluorescence microscope, though over here it has been regarded as a separate type of microscope, but it is a special type of optical microscope. Okay. Okay. So in this optical microscopy, what happens? In this optical microscopes, they basically use lenses to refract the visible light that pass through a thinly sectioned sample to produce an observable image. Okay, so as I told you, pass through a thinly sectioned samples. That means the light from here, it is transmitted through the sample. So these optical microscopic techniques usually they work in the transmittance mode. However, there are various other optical microscopes which have been developed at a later stage. They work in the reflectance mode. Okay. However, when we talk about optical microscopy, we usually understand that the microscope will be working in the transmittance mode. However, when we talk about this reflectance mode microscopy, we either call it reflectance microscope or epiluminant microscope. So the reflectance microscope and the epi-illumination microscope, they are both meaning the same thing. Okay, that means if I say you that there is an epi-illumination microscope, that means the microscope is working in the reflectance mode. Okay. And fluorescence, we all know that it is a special type of optical microscope, and we have already studied about the fluorescence. The mechanics of fluorescence is known to us. Okay, so what it does, what we do is over here is that we have some fluorescence tags which are being attached to the sample, and then we excite the samples with a specific wavelength of light, and then we have a specific band of light being emitted at a higher wavelength, and that higher wavelength light is being captured and the imaging is being performed. Okay. In the case of electron microscope, as the name suggests, we need to use a beam of electron. Okay. So the electron microscope, it would be using a beam of electron to visualize the samples, and just like in the optical microscopy we have the transmission and we have the reflectance mode, in electron microscopy we have TEM, transmission electron microscopy, and SEM, scanning electron microscopy. TEM, as the name suggests, it would be just like the normal compound microscope where the electron beams will be passing through the sample, whereas in the scanning electron microscope mode, the instrument will be working in the reflectance mode, and we will be able to look into the surface topography of the samples. Then there are another type of microscopy, scanning probe microscope. In this microscope, we have AFM microscopes, atomic force microscope, and these microscopes, they work in the scanning probe using the scanning probe method. However, in our course we do not have this AFM microscopy, so we will not be discussing about the AFM microscopy. However, if I get some time, say if I get 1 or 2 class extra at the end of the course, then I will try to cover this AFM microscopy. Okay, because this is also an important type of microscopic technique which is used in biology. Now coming to the optical microscope, this optical microscope, as I told you, it uses visible light, hence they are also regarded as light microscope. Okay, and as I told you, it commonly uses visible light. Okay, so it uses a system of lenses to generate magnified images of small objects. Okay, this type of microscope are the oldest design of the microscope, and believe me, the first microscope, that was the compound microscope, that was being developed in the 17th century. We have the same basic architecture till today. So you can understand what revolution it has been brought in the 17th century. It's still serving our purpose to explore the unseen world of the microbes. Okay, so understanding or studying the microscopy, it's a beautiful subject. Okay, so as I told you, so object is being placed on a stage and may be directly viewed through one or two eyepieces. If you see over here in this basic architecture, what I have drawn is that there is one eyepiece lens. Okay, however, there are various microscopes which uses a special kind of arrangement over here, so that you have a pair of eyepiece lenses and you can see the same image through this pair of eyepiece lenses. And the microscope which are having a pair of eyepiece lenses, they are regarded as binocular microscope. Okay, and the microscope which uses only one eyepiece lens, it is called, since it is having only one eyepiece lens, it is called monocular microscope. Okay, so one eyepiece, monocular, binocular. Okay, in this type of microscope, if you are using the binocular microscope, both the eyepieces, they typically show the same image. But with a stereo microscope, it is a another type of microscope, optical microscope. It shows slightly different images and have been used to create 3D effect. Okay, to understand or to have a 3D effect while you are visualizing the images. Okay. In the current day world, if you want to analyze or capture the image, then we need to use a camera, and that image what we capture, that is regarded as the micrograph. So a micrograph, it is not a graph, however it is the image of the microscopic area. Okay. The sample can be lit in a variety of ways. Transparent objects can be lit from below, and solid objects can be lit with light coming through or around. So when the light is coming through the system in the parallel fashion like this from the source, and it is being collected by the condenser, then it is called bright field. And around means, say you are having a source and suppose this light is coming like this. Now suppose you use a blocking system over here. So what it would do is that it will block the light from the central part of the source, and you will be getting the lights from the periphery of the light source. Okay, so if you try to look into the what you call top view of this source, suppose you are having this source and light is coming throughout this whole section, then it would be regarded as the bright field. And if you use a blocking system, something like this, so what is happening over here? the light is only coming through this green highlighted area. Okay, then this system, it is called dark field illumination system or dark field microscopy. Okay, so as the system, they can be lit from the light coming through, that is called the bright field. That means all throughout the source the light will be coming out or around the objective lenses. So if you block it over here, so you will be getting the central part of this light will not be going through the objective lens, and around the objective lens, or I mean to say from the periphery of the objective lens, you will be getting the light entering into the objective lens and the tubular section. So over there, in that way, if you get the lights entering into the optical system, then it is called the dark field imaging. Then we can have polarized light. It may be used to determine crystal orientation of the metallic objects. Okay, so we all know that polarized sheets are available. So if you have a polarized sheet, and if you look over here, so if the light comes from the back, it passes through here. If both the sheets, they are in the parallel position. PRALLEL, parallel position. However, suppose these polarized sheets, they are in the cross polarized fashion. They are in the cross they are present as the cross polarized fashion. Then the light from here will not be able to pass from here. Okay. However, in that case, if you place some crystalline materials in between, what they will do, they will change the polarization of the lights which are interacting with the objects. Okay, so there is a change in polarization, and when there is a change in the polarization, then this second polarizer or the polarizing sheet, which is regarded as the analyzer, it allows these light rays to pass through it because they have changed the polarization. And if you image those systems, then those systems, you will be getting the polarizing effect in the microscopic structures. As we go through, we will see how it helps us in looking into the images of different crystalline products. Say for example, sugars. It is a crystalline material. It will show polarization. Salt. It will show polarization. Fats. It would show polarization. Okay. So this polarization, it helps us in understanding the microarchitecture in a better way, which the bright field microscopy may not have been able to provide us the information with. Okay. Then we have a special kind of bright field microscopy which is called phase contrast microscopy. It helps us in increasing the contrast of the image by highlighting small details of differing refractive index. Okay. Now coming to the optical diagram of the simple microscope, I have already told you. So you have the object over here. So if you place it just nearer to it, you will find that an amplified image is being formed. So this is the optical arrangement of a simple microscope. Okay. However, in the case of compound microscope, I told you there are two objectives. First one is the objective lens and second one is the eyepiece. So initially you have this object, then the light from this object are being collected by this objective lens, and if you see, it forms an inverted image within the optical path or optical tube, within the optical tube of the microscope. Okay, and then that image, it is acting as the it is acting as the object for the eyepiece lens, and then we have a greater magnification over here. Okay, so this is how the optical system of a compound microscope it works. In both the things, if you see, you have this object and the image has been magnified. In the second case, since there is a dual magnification, due to this dual magnification, the amplification or the magnification of the image is quite high. Okay. Now this is a typical microscope. So this one, these are the eyepiece. Okay. Now if it is a binocular microscope, you will be seeing that there are two eyepieces, whereas in the case of monocular microscope, you will be having only one eyepiece. Then we have objective turret, which is also regarded as the revolver or the revolving nose piece, which holds multiple number of objective lenses. So these are these steel items. These are the objective lenses, and this black item, it is called the objective turret. Okay, objective turret or objective revolver. Okay. Then next we have the objective lens. I have already shown you the objective lenses over here. Then we have focus knobs. So we are having this 4 and 5 are the objective knobs. So these objective knobs, these 4, the inner part, it is the coarse objective knob or the coarse adjustment focus knob, and this 5, so it is the fine adjustment focus knob. Okay. Now these are coaxial knobs. These are coaxial knobs. Okay. Then we have a stage. So this is the stage where we keep the sample, and then we have a light source. This is the light source. Then we have a diaphragm and condenser. So we have a condenser and diaphragm over here. Here, right? In this mechanical stage, we are having the 9. Okay. Oh, sorry. This is the mechanical stage. This is the stage to hold the specimen, and then we have the mechanical stage which will move the stage. And again, if you see over here, which has not been marked, there is a what do you call stage attachment. And if you see, there are 2 rings, 2 knobs. The first knob is over here, say A, and the second knob is the bottom one. So these 2 knobs, it helps us in the movement in the XY direction. Say, so in this X direction, sorry, in this X direction, and another knob, it will help you in the movement in the Y direction. Okay, so that you can select the position of the sample which you want to analyze. Okay, and this is a basic monocular optical transmission microscope. And if you see over here, nowadays this illumination system, it uses either LED lamps or halogen lamps. Okay. Previously, if you remember in our schools, many of us might have seen the mirrors. So this mirror, it collects the light from the sun or from the tube light, and then it reflects the light into the condenser. Okay, they do not have any electronic lamps over there. Okay, however, if you want, you can convert this easily over here using you just need an LED light. So you have a LED light, you then attach a potentiometer and the pot, you put it into an enclosure, and then you give a diffuser over here. Then we have a diffuser, you can put a diffuser and you can attach it very easily over here, and you can upgrade your this monocular optical microscopes into a this electronic microscope. Okay. Further, we can attach some modular microscope cameras, sorry, not microscope, modular cameras in the eyepieces, and it can help us in converting both the binocular and the monocular microscopes into digital microscopes. Okay. Then coming to the this mathematics of the microscopy. So we have limit of resolution. This limit of resolution, it is given by D, and it is given by 0.61 lambda n sine alpha. Okay. So 0.61, it is a constant. Then lambda, it is nothing but the wavelength of the light. Then n, it is the refractive index of the material, of the optics material. In this case, we usually use glass. Okay, and then sine alpha, it is basically the angular aperture. So what is the angular aperture? Suppose you have this specimen over here, then the light, it is coming in the form of a cone, and this angle, it is called alpha. Okay, so that is called the limit of resolution. So what is this limit of resolution D? The limit of resolution D, it is nothing but, suppose you are having two point objects which have been placed D distance apart, then what is the minimum distance D which your microscope will be able to resolve? Okay, so what I mean to say is that suppose over here we are having these 2 points, we are able to image it properly. Now in the second instance, we bring this closer, still we can see that there is a gap. So these dot or the point objects, they are being resolved. Then next, again if we move it this closer, and over here if you see, we are not able to distinguish these two particles or the 2 point objects as the separate objects. So we can see there is a limitation at our end. The same thing happens in the case of the optics also. When we try to bring the point objects closer and closer, there would be a minimum value of D which can be resolved, or this minimum value of D where we will be able to image 2 point objects, and that is called the limit of resolution, and it is given by this function 0.61 lambda divided by n into sine alpha. Now this limit of resolution, it is what do you call, it is inversely related to the resolving power. Okay, so when D is minimum, that means our resolving power is higher. Okay, when D is minimum, our resolving power, it is higher. Okay, so if we say our resolving power, it is equals to, because it is equal to 1 by limit of resolution, we can write it down that n into sine alpha divided by 0.61 into lambda. So if you see the wavelength lambda, if lambda increases, our resolving power decreases. So if we go towards higher wavelength systems, like towards the higher systems, then there will be a decrease in the resolving power of our microscope. However, if we try to come towards this violet, indigo, and all these wavelengths we choose, then the resolving power, because this violet, indigo, they have a smaller wavelengths, as it starts from say 400 nanometer. Okay, so they are having lower wavelength, and since they are having the lower wavelength, our resolving power of the microscope would be the higher. Also, this factor n sine alpha, it is also regarded as the numerical aperture of the system. It is regarded as the numerical aperture of the system, and Na is basically given by, it is regarded as the measure of the ability of a lens to collect light from the specimen. To collect light from the specimen. Lenses with low Na collect less light than lenses with high Na. Okay, so you need to remember over here, if lenses they are having low numerical aperture, they will be collecting less light, whereas if there are any lenses which are there, you will be getting which is having higher numerical aperture, they will be collecting the higher amount of light. So if there is a higher amount of light, the quality of the image would be better. So for both these condensers, your condensing lens and these objectives, you will find that each objective lens and each condensers, they are having, or they are provided with a numerical aperture. Okay. Then, as I told you, eyepiece, they are also regarded as the ocular lens, and usually we have 5x, 10x, 15x, 20x, and 25x eyepiece lenses. However, the 10x eyepiece lens, it is the most common objective. Okay. In patented and good quality microscopes, you will find that the objective lens and the eyepieces, they are matched to give best possible optical performance. Okay. However, these are quite costly, and this commonly occurs with apochromatic objective lenses. Okay. However, these are quite costly. Okay. Then objective turret. So it holds a set of objective lenses, and it helps us to switch the user from one objective lens to the other objective lens. Then the next objective, then we comes to the objective lens. So we can have from 5x to 100x magnification lens. In many microscopes, you can find 4S objective lens also, and they have a this numerical aperture in a of in between 0.14 to 0.7, and they have usually a focal length of around 40 mm to 2 mm respectively. The objective lenses with higher magnifications normally have higher numerical aperture and a shorter depth of field in the resulting image. Okay, then oil immersion objectives or water immersion objectives are used for greater resolution at higher magnification. Okay, so why this is so? And there is another information which has been included over here, that is called the depth of field. Okay. So I think we are near to our only 5 minutes are left. So there is one understanding which we will be discussing in the next class, which I should have discussed today, but due to the shortage of time, I cannot discuss it today. So when I start the next class, please remind me that we need to discuss about the depth of field. Okay. Then these immersion objectives, they are used with index matching material such as immersion oil, water, and a matched cover slip between the objective and the lens, and they allow us to capture as many light as possible. Yes? Do you want to ask anything? So refractive index of the index matching material, it is higher than the air, and it allows us that the light that is transmitted from the specimen to the outer face of the objective lens with minimal refraction. Numerical apertures may be as high as 1.6. The larger numerical apertures allows collection of more light. Okay, and oil immersion lens usually has a magnification of 40 to 100x. Okay. The light sources, they can be either daylight, it can be directed via a mirror, as I told you. There can be a halogen lamp, there can be LEDs, it can be lasers. Then we have some color illumination. These color illumination systems, they are uh, available in very expensive microscopes. However, when we talk about our day-to-day normal routine laboratory exercises, we do not need this color illuminating system to that extent. Okay, then this gooseneck dual gooseneck illuminator, these are there. So if you want to give extra light, suppose you are having a transmittance microscope and you want to see the topography, then what will happen? If this topography, if you want to see, then uh, this the samples for which you want to see the topography, they are usually opaque, and hence these samples, they will not allow the transmission of the light through over here. Now these gooseneck illuminators, there may be a single gooseneck illuminator over there. You will be having only one arm, and usually dual gooseneck illuminators are used. And now these dual gooseneck illuminators, they can spread light onto your sample, and then you will be having these objective lenses which will be collecting the information from the system. Okay, these are there. So this type of illuminating systems are used. Then different types of immersion medium. So air, it is having 1, and as you see, water, it is having 1.33. Then we have glycerol, which is 1.47, and the higher the refractive index, higher will be the ability of the system which can collect the light from the specimen to the objective lens. Lastly, we have the condenser. Condenser, it is the lens designed to focus light from the illumination source onto the sample. The condenser may include diaphragms, filters, which allows us to manage the quality and the intensity of the illumination. And then for different illumination techniques like dark field, phase contrast, and differential interference contrast microscopy, additional optical components may precisely be aligned in the light path. Okay, so with this, I will stop today.